Okay, so I'm recording now. First slide of the chapter, what is organic chemistry? In chemistry, there's a lot of what we would call sub-disciplines or a lot of, types of chemistry. It's like in physics, there's like astrophysics, and then there's, the physics of kinematics, like the motion of an object. In chemistry, there's a lot of different, what we would call sub-disciplines. So you can be like into forensic chemistry, which is kind of like, the what you see on TV shows like CSI, where they're like trying to test, samples of clothing for blood or something like that. There's analytical chemistry, very much like forensic, where, maybe you would test for the amount of vitamin C in a glass of orange juice, or you might test for how much caffeine is in a Red Bull. Analytical chemists kind of look at studying what chemicals make up a product. Organic chemistry looks at the structure, property, and reactions of what we would call organic compounds. So this is matter that is carbon-based. So what are some examples of this? Well, organic compounds, they form the basis of all life on Earth. So like I said, plants and animals, from humans to birds to fish, they are all carbon-based compounds, very structurally diverse. And I don't even mean living things. I mean chemical compounds that are made of carbon are very, very diverse. And they either form the basis or important parts of products, including plastic, drugs like pharmaceuticals, petrochemicals, food that we eat, explosive materials, paints, dyes, perfumes. I mean, the list goes on. Organic chemicals are really, really one of the most important chemicals in your everyday life. I mean, just take plastic. Right? Anything that you have that's made of plastic is made from, typically made from organic chemicals. So carbon, why is carbon so cool? Why is carbon so amazing? There's a lot of reasons, but if you guys can remember back in chemistry 1120, and I know some of you I taught in 1120, do you guys remember Lewis dot diagrams? It's on the next slide, but if you guys can remember your Lewis dot diagrams, carbon has 4 bonding electrons. So it's one of the best chemicals, or most diverse chemicals in terms of bonding. There's so many ways that carbons can bond to each other. They can be in single chains, they can be in rings. It's actually quite amazing. So carbon, group 6A, has 4 valence electrons. In a compound formation, 4 additional valence electrons are required to fill this octet. So let's take like the most classic of the carbon chemicals, methane. And don't worry, guys, you don't have to worry about these diagrams in this course. This was from 1120, so you won't be seeing this again. But this would be an example of a full octet of carbon. In kind of simple words, the reason carbon is so good is it's like it's the best Lego piece of ever, right? You guys know what I mean by Lego, right? Like building blocks. Carbon is one of the best pieces. There's so many different ways we can stick carbon together. It's really, really cool. All right, sorry, I'm just trying to open up my chat here. Give me 1 second. Just trying to open up the chat menu. I know there was some messages in there. Okay. Iman, I had a question from Iman there. I might teach chemistry 3. I normally do teach chemistry 3, which is, and that's a really relevant question, because this is basically the beginning of chemistry 3. So if and when you guys get to chemistry 2420, the third and final chemistry course for you guys, this is kind of what it's, excuse me, what it's about. There's no math, there's no calculations. It's all about carbon. It's a pretty cool course, and I do typically teach it. So back to this. Hold on, guys. I just got to clear my throat here. Sorry, didn't want to cough into the mic. The bonding of carbon, the additional valence electrons are always obtained through covalent bonds with carbon. So the bonding of carbon is done covalently, and it can form different types of bonds. You can have single bonds, double bonds, and triple bonds. And again, this is where the diversity, or the different amounts of chemicals can come from. Something like a double bond, whoops, sorry about that. So like a single bond, we would call this ethane. I'm not going to worry about the hydrogens right now. We'll talk a little bit more about that later. A double bond would be ethene, and a triple bond would be ethine. Now, I think, let me fix this one here. This is A-N-E. In theory, you could have a quadruple bond, but I've never seen it. I've never heard it talked about. So typically, carbon chains have 1, 2, or 3 bonds, and we call them alkanes for single bonds, alkenes for double bonds, and alkynes for triple bonds. And we'll talk a little bit more about that, maybe not today, but in the next class. We don't go too deep into this topic in this course. Chemistry 1121 is pretty diverse, so we only kind of touch on the surface of this. And then for you guys going into chemistry 3, we'll look at this a lot more, like a lot more. Okay, so section 1 was basically, what is organic chemistry, and why is carbon important? So how do we apply this? Well, one of the major chemicals, we'll say, in the Middle East, especially in Qatar, would be hydrocarbons. This is where the kind of the money in this country comes from, is from exporting things like, well, hydrocarbons. So the big thing in Qatar is liquefied natural gas, LNG. LNG is natural gas, so methane or ethane, that has been turned into a liquid so it can be shipped overseas or anywhere really on Earth. It's pressurized or compressed down until it forms a liquid. It's kept cool, and then it's shipped all over the world. It can be shipped on boats or by train. Typically with Qatar, especially with the blockade, it was all shipped via boat. So hydrocarbons, really important chemical. And actually, where I'm from, hydrocarbons we're kind of from very similar places, just very different as well. What I mean is I'm from like a very small part of Canada. So Qatar is a pretty small country. I'm from a pretty small place in Canada. I'm on the Atlantic Ocean. You guys are on the ocean as well, but in the Gulf, but still near the ocean. And a lot of our economy comes from drilling for offshore oil products. So where I'm from, there's a lot of my friends and family work in oil, not refineries, but oil wells or oil extraction places. So it's kind of similar to here, very heavily economically based with oil or hydrocarbons. So hydrocarbons are compounds, and this is one of my favorite definitions in all of chemistry. Hydrocarbons are compounds that contain hydrogen and carbon. That's it. That's what a hydrocarbon is. So again, when you guys think of hydrocarbons, you should be thinking of oil and gas type of products, methane, propane, octane, things like that. There are 4 basic types, categories, I guess I should say, that you can place hydrocarbons in. There are single bonded alkanes, double bonded alkenes. I'm going to show you pictures of this in like a second. Triple bonded alkynes, and then one of my favorite is called aromatics. Now, the word, if any of you are familiar with the word aroma in English, it means like a scent, and typically it's a good scent. So an aroma, when I say scent, I mean like a smell. Aromatics are traditionally or typically heavily scented or very strongly smelling chemicals. So a lot of the food you eat has aromatics in it, and that's where you get
Okay.
smells like vanilla or cinnamon. They're aromatic. Yes, there's a question.
Like benzene, right? Aromatics.
Yes, exactly. Literally, exactly. The student just said, I didn't get to see your name. It's okay. Benzene. Sorry, what's your name?
Hadi-
Okay. My computer is kind of being a bit slow here, but yeah. This is benzene, and benzene is an aromatic. So how do I explain that simply? Like all aromatic compounds have a benzene ring. Okay, and it's the exact same thing. Benzene rings are so important. You see them in all sorts of chemicals like caffeine and coffee. And I mean, aromatics are such a common compound, and they're very different than the other chemicals on this list. So let's look at some pictures here. Alkanes have a single bond. Okay, so I'll just write here single. Whoops. Anybody who had me last semester knows my pen likes to do that from time to time. Alkenes have double bonds, meaning they're bonded together covalently twice. Alkynes have triple. And aromatics have what we call a benzene ring. So this would, I don't really want to say the word ring here. It's really important that I say benzene. And I can explain that in a second. There's a difference between a ring and a benzene ring. So let me just explain that. I'll just give you guys a second to kind of absorb the information on this slide, and then I'll show you the difference between like a ring and a benzene ring. They're not the same. And honestly, like we don't really have to go into too much detail in this course because it's not that important. But in chemistry 2420, your third chemistry course, we'll look at this a lot more. All right.
Mr. Mark, the
Yes.
last one, benzene ring?
Yes, benzene ring.
Okay.
Yeah, sorry for my spelling there. Abdul, before I go on to the next slide, there's a few things. Actually, wow, there's a lot of things. Sorry. I'm not getting notifications that I'm getting chat messages. I'm sorry, but I can see the chat. So there's 3 messages I want to address. Let's start from the bottom. Will you have to do hydrocarbon naming? Yes, and I'll explain that on the next slide. It's not near as bad as you think it is. So Abdul Halim or anybody who's ever named hydrocarbons before, it can be crazy. We're going to keep it simple in this course. I'll show you on the next slide. Then Maria mentioned that benzene is a hexagon. Absolutely, it is a hexagon in shape, and there's something kind of special about it. And then finally, this is a good question. Does diamond have hydrocarbons? And that's a really interesting concept. Diamonds, okay, I could talk about this for a little bit, but I know that this culture, or I know that you students, you don't like to use pencils very much, which is always surprises me. I never get used to it. Where I'm from, we only use pencils, and pens you would use to like sign a document, sign a legal document, but we always use pencils. And the reason I'm bringing this up is chemically, a pencil and a diamond are very similar. And what I mean specifically is the lead of the pencil. So that, the black or gray part of the pencil that you use to write, that's called what we would call a pencil lead, but it's not made of lead. It's actually made of carbon. Charcoal, if you guys, have a barbecue out in the desert and you might use charcoal. Charcoal is made of carbon as well. So are diamonds. Diamonds are actually pure carbon. So what's the difference between like a diamond and a pencil lead, or a diamond and a piece of coal? It all has to do with temperature and pressure. So diamonds are typically found deep under the Earth's surface, where it's very warm and the pressure is incredibly high. So if you took a pencil lead or a piece of coal and did the exact same thing, deep under the Earth's surface under high pressure, you could turn or convert that coal into a diamond. And the last thing I'll say about diamonds, I'm not into jewelry, if you can believe it. Even though I could talk about diamonds for a long time, I just find it very interesting that coal and diamond are the same chemically, or for the most part. One thing I've also read is you can get diamonds that are made in the lab. So, you can get diamonds that are what we would say not natural or synthetic. And one of the ways that a jeweler or an appraiser or whoever, would look at the diamond would know that the diamond was fake or made in the lab is that it would be too perfect, which is really interesting to me. So diamonds that are made in labs, synthetically, have very minimum to no imperfections, whereas diamonds that you would find in real life have imperfections. Anyways, I could talk about this for more, but yeah, a diamond is made of hydrocarbons, or specifically carbon. Very, very interesting. Or well, interesting to me anyways. Now, I won't do too much more today, but guys, because it is on this class, Sunday's class, I won't go too long. I've been teaching since 9:30 this morning. I'm sure you guys have been in class since 7:30, 8:30, 9:30, I don't know. But I won't go too much longer on Sundays. But I want to explain to you the difference between a ring and benzene. Whoop, sorry. Okay. So in chemistry, you can have lots of different rings. You could have a butane ring. We would call this cyclobutane. It looks like a square. You could have cyclopentane. It looks like a house. And then, of course, you could have cyclohexane. So as Maria said, it's a hexagon. I used to be so good at drawing these, but I hate saying this, but when I was your age, in my early 20s, I could draw benzene rings like with my eyes closed, or cyclohexane anyways. So these are rings. These are not benzene. Okay, a benzene ring is this and only this. It's a hexagon, like Maria said, but every second bond is a double bond. And sometimes, just to make life easier, instead of writing every second bond as a double bond, what a lot of chemists will do is put a circle in there. That is what benzene is. It's a hexagon, so a six-sided figure, but every second bond is a double bond, and a lot of times scientists will just put a ring in the middle to represent its benzene. So like these guys on the left, these are not benzene. Only the thing on the right is benzene. And you guys might not realize, or you might not think that, what's the difference? Abdul Halim, yes, you can definitely draw a circle inside, no problem. But a lot of you guys, sorry, I just got rid of my screen there. But a lot of you guys might think, what's the difference? Like, why do these double bonds or this ring in the middle, why does that even matter? Though, and this is something that we'll talk more about if you guys get to Chemistry 2420. it completely changes how the chemical reacts. Benzene rings are very unreactive and stable. They don't like to react with other things, but that's for another course. But Abdul Halim asked, if you had to draw a benzene ring, could you just do the circle inside? Absolutely. So that's perfect. I don't think you guys will have to do a lot of drawing in this course. I really doubt it, but if you ever had the situation where you had to draw a benzene ring, the circle is fine. All right, I'm almost done. Again, on Sunday's classes, I won't go too long because it's a long day for me, and I'm sure even longer for some of you. So I can't remember who it was in the chat. Let me just see if I can open it up. But somebody asked, it might have been Abdul Halim. Yeah, will you have to do hydrocarbon naming? You guys should know, and again, when I say hydrocarbon naming, I just mean this list here, the first 10 members of what we call the homologous series. So this is probably the first major thing in Chemistry 1120 that you guys should know. This will definitely come up again as like a multiple choice or something in your lab. You need to know the name or the names of the first 10 members, I guess I could call them, of the alkane series. Now, what do I mean by that? And what do I mean by homologous series? There's some big words on this slide, but all I mean is if we took a carbon molecule or a carbon atom and then continued to add carbon atoms to that, it would change the name. 1 carbon is methane, 2 carbons is ethane, 3 is propane, and so on. So you guys need to know this. I put a circle around it, but I'll do it again. You need to know the numbers 1 to 10. Anybody who had me last term, so like Aman and Maria and some of the others, you guys know I'm not big on making you memorize things. I was never a fan of memorizing things in my chemistry. I like, understanding or using math or something like that. I didn't like memorizing. This is one of the few things you have to memorize. It's not in your data booklet. It is incredibly important that you know this for Chemistry 2420. All right, let me just see what's going on in the chat here, and we're almost done. I think I'm going to do maybe 1 or 2 more slides, and then that's it. Ooh, that's a good question. So Aman asks a question. These are the same as the Roman numerals. And for the most part, yeah. Like chemistry kind of pulls from a lot of things. So like Greek prefixes, Roman numerals, there's German on the periodic table, there's Arabic. Actually, we're going to learn an Arabic word in a second on the next slide. So like chemistry takes from everything: English, German, Arabic, Greek, Latin, and these are very similar to the Greek prefixes or even Roman numerals, whatever you want to say. I think they're probably closer to your Greek prefixes. You'll notice that a lot of these are shapes that you would have done in mathematics. So a pentagon is a 5-sided shape. Right? So how many carbons does pentane have? 5. Hexagon, 6-sided shape. Heptagon, 7-sided. The octagon has to be my favorite, or octane, sorry, because I'll never, ever forget that octane has 8, right? And if you guys watch MMA or UFC, an octagon is an 8-sided ring. If you're like me and you like animals and sea creatures, an octopus has 8 tentacles. So a lot of these I just naturally remember, but there are a few like ethane and propane and butane you guys might have to remember. Also, one more thing before I'm going to finish it. I'm going to do maybe 2 slides and we'll finish. I, as a North American, as a Canadian, and basically Canada is kind of like America Junior. I say methane. If you guys had maybe a British teacher, or even I've heard people in the Middle East say methane, it's the same thing. It's just as a North American, we say methane. But methane, methane, it's the same. Okay, just don't let my pronunciation confuse you. So I'll just read it out one more time. Going from 1 to 10 carbons: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, which is easy because it's like 9 or non, and decane. All right, make sure you know these. These will, I know you can't see my face, but I'm winking right now. Wink, 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 wink. This will be on a multiple choice for sure. I might ask you what you would call a carbon with, a chain with 5 carbons, pentane, or I might say, what would you call a chain with 8 carbons, octane. One last thing, sorry, and then I'll move on. These are all alkanes. These are all single bonds. If you introduced a double bond here, then you would change the name. So it would be ethene, propene, butene. It's really a cool system, I gotta say. Okay, so, well, I won't finish this. I think we've had enough for today, but let me just kind of introduce the next part, and then we'll finish for today. All of these lessons will be going up on YouTube. Hadil asks, do you have to know the structural formula? No. You would have to know the number of carbons, but you don't have to worry about the formulas. Okay, so in terms of name, or in terms of what you need to know, like, you don't even need to worry about the boiling point, which is another topic I could get into in great detail. But you need to know the name and then how many carbons it has. That's it. You don't need to know anything else. So again, if I said, you had a chain of 7 carbons, what would you call it? And hopefully you would say heptane. Okay, so I'm almost done. I think very quickly, I'm just going to show you the 3 ways that we can express a formula, and then I'll explain this in more detail tomorrow. Well, not tomorrow, whenever we have class again. When do we have class again? Tuesday afternoon. Gee whiz, I got you guys pretty late. Sunday, 4:30, Tuesday, 3:30. Oh, well. Anyways, so in terms of representing an organic molecule, it can get very complicated. Let me just show you one of my favorite molecules. I just stopped my screen sharing for 1 minute. You'll see why in a second. So I'm going to show you one of my favorite organic molecules ever. Some of my students I had last term probably know the answer. It's caffeine. I love caffeine. So without like tea or coffee, I don't know if I would function most days. It's one of my favorite chemicals, probably not bad for me. It's a central nervous stimulant, so I don't think too much caffeine is good for me, but without my coffee, I wouldn't be able to live. Well, that's not true. Without my coffee, I would be a very grumpy man. Let's say that. And look at the molecule of caffeine. Okay, I mean, there's a lot of, we could take like aspirin, which is a painkiller, like in Panadol. Here's the chemical formula or structure of aspirin. The formula is typically towards the bottom. Here it is. Let me zoom in so you can see it. So like in chemistry 1120, you might have called the formula C9H8O4. But that doesn't really tell me much, right? I can figure out the molar mass, yes, of course, but it's not the formula that matters in organic chemistry. It's the shape, and that formula does not at all explain this lovely, beautiful shape. You'll notice that aspirin here has a benzene ring. It has oxygens in it. It has all sorts of different special things happening. So for formulas or organic formulas, we need another way to represent them besides, and let me just open up my notes again, besides what's called your chemical or general formula. Hold on, I'm just going to share my screen again. Okay, that's all right. So in Chemistry 1120, you guys learned about the general formula. And this is a chemical called propanol. This is a chemical that that we would classify in chemistry as an alcohol. An alcohol in chemistry isn't what you think it is in like real life. An alcohol is anything in chemistry that has an OH. Okay, there's maybe not millions, but there's thousands upon thousands of different types of alcohols in chemistry. So it's not kind of what you hear, you know, the alcohol you hear in everyday life. An alcohol in chemistry is any chemical that has an OH. And that word comes from, like anything in chemistry, like alkali metals, alkaline earth metals. Alcohol comes from Arabic language. Now, I don't know what it translates to these days, but anything in science or math or chemistry, like algorithm, algebra, aldehyde, I mean, there's so many that start with Al, they're typically from Arabic. I wonder if I Googled this. Where did word alcohol come from? Arabic word alcohol, A-L-K-O-H-L, referred to a fine black powder used as a dark eye coloring cosmetic. Interesting. So Google, or that's according to Google anyways. I don't know how true that is, but yeah, anything you guys see in math or science that starts with AL, algorithm, algebra, comes from the Middle East. Pretty impressive. So this makes me sad. In organic chemistry, this doesn't tell me anything. We can expand, I will cover this, I promise, a little bit more detail tomorrow. So for anybody feeling I'm rushing this, I am. I'm just trying to finish this off so we can look at this tomorrow. There is another way to expand this where we can kind of write what's called a condensed formula. So it's not the general formula. It does show a little bit of the shape. But then there's the structural formula. This makes me very happy. The only problem with this formula is it would take you a long time to write. But the reason I like this formula is it shows me the shape of the molecule. Do you guys remember back in chemistry 1120, you know, tetrahedral, trigonal planar, linear, and all that? That's what you can tell from the structural formula. The only problem with the structural formula is it takes a long time to do, right? And in math, science, chemistry, physics, we're always in a rush. So how can I talk about this formula without writing all of these letters or without writing all of this shape? Well, there's the ultimate called the skeletal formula. And like, think of your body, right? You are a mass of flesh and fat and muscle and tissue surrounded by what's called your skeleton. Or sorry, that surrounds what's called your skeleton. If you drew a human figure and only drew the skeleton, you still know it's a human, but you really saved a lot of time. You didn't have to draw the shirt or the hat or muscles or anything else. So the word skeletal formula comes from the concept that even looking at the skeleton of something, you know, if I go to a museum and I see the skeleton of a dinosaur, or I see the skeleton of a polar bear, I can tell what that creature is, but I don't have to look at the fur and the skin and the organs. That's like that in chemistry. The skeletal formula is the backbone, and it's the formula that quite simply shows that this chemical has 3 carbons, 1, 2, 3, bonded to an OH. So looking at this little tiny diagram here, this little tiny formula, I instantly know that this is propanol. It's propane, 3 carbons, bonded to an alcohol. So I call it propanol. And we'll talk more about that tomorrow. I think I'm going to finish there for today. Iman and Maria have 2 very good things. So the suffix, I'm very happy to hear the word suffix. The suffix, which means the ending of the word, OL, defines it as an alcohol. If in chemistry we use the suffix like ONE, own, so like propanone, that would be a ketone. There's so many suffixes. It's hard when you're dealing with such a small chemical, but yeah, Maria, you're correct. And Aman, alcohols, I think, are typically weak acids. So the question was, is it a base? And actually, I'm very happy you said that. Before you guys go, Aman asked, is it a base? And I know what you're thinking, because if you think of like NaOH or CaOH2, these guys are like super strong bases. But alcohols are actually completely different because they're not ionic. Typically, alcohols are what we would call weak acids, and that's something we can talk about another day because it is 5:18, and I'm sure you guys want to go get some dinner or take a break from today. So guys, that's it for me today. I will cover this a little bit more tomorrow, or sorry, on Tuesday. I'll go over like, you know, the differences between condensed, structural, and skeletal. And then we'll talk about functional groups, which is things like alcohols, ketones, aldehydes. It's one of my favorite topics. So guys, that's it for me today. If you have any questions, let me know. Aisha, the recorded lectures, I will send you a link very shortly. I put them on YouTube. And I don't have the link yet because I haven't really recorded a class until today. I did record this class. So once I get that uploaded to YouTube, I will send you the link. So you can look for the link in a few days. Thank you, Harold. Thank you, Samar. Thank you, Aman. Thanks. Have a good night, Abdullah. Does someone else have a question? Thank you, Aaron.
Yes. Sir, had you took the attendance?
Yes, attendance has been taken. No problem.
Okay, thank you.
No problem.
Thank you, Mr. Mark.
Thank you, sir.
Thanks, guys. Have a great evening. Abdul Halim, you have a question outside of today's subject. You can ask that whenever you want.
See you, sir.
Thank you. Have a great evening, Yasmin and Aisha and everybody. Ooh, Abdul Halim, the answer to your question is yes, but okay, so for anybody sticking around and is curious, Abdul Halim asked the question, will we ever run out of oil and natural gas? And the hard answer to that is yes, but I'm going to put an asterisk there. There's a couple of factors that we need to consider. First thing we need to consider is that as we progress, as you know, we move forward with technology, we're finding substitutions for oil and gas, meaning like instead of using oil to create energy, we can use solar power. Instead of using oil to make plastics, we can use things like biofuels, like or different chemicals. So that's one thing to consider, because if we use less oil, it will, you know, last a lot longer. Number two to consider is technically oil is not a renewable resource, meaning like it's not coming back as fast as we use it. But in terms of how much there is, we have decades and decades of oil left. So let me just see. we run? Okay, so if you like Google this, how long until we run out of oil? I'm a huge fan of using Google for everything. So globally, this is from a couple websites actually I have in front of me. We're using about 11 billion tons of oil every year, but we are using less, I think, over time once we start using alternative technology. However, they predict that the oil deposits could run out in 50 to 60 years. Again, that's a big could. I'm not saying it will, but at this rate, it could be in 50, 60 years. So you might be alive for that. I don't know if I will. I'm pretty old. But yeah, so it's a really good question. It's not something I would worry about though. Like I know where I'm from, we rely heavily on oil and gas. I know the Middle East does as well, but I think between now and 50, 60 years, things are going to be a lot different and maybe for the best. I know Qatar has really diversified their investments, right? So UAE, Qatar, even Saudi are trying to like make sure if and when the oil runs out, or maybe it never runs out, maybe the world just stops using it. They have backup plans for all of this. So yeah, it's something I'm sure some of your other instructors would know more about it, but there you go. Thanks, Abdul Halim. And anybody sticking around, have a great day. I'm gonna go eat some dinner. So I'll see you all on Tuesday. Have a great one. Bye-bye.